All right. Good afternoon. So my name is Herremans. I'm from Imec. And I'm here to talk about an application domain of chiplets, so really the automotive space. I'm not sure what kind of audience I would have, and I see a lot of servers out here, so I wasn't sure to what extent you guys would understand, okay, why are we talking about chiplets in automotive? And let me start with defining what is today's vehicle is typically called a hardware-defined vehicle. And the reason why people call it hardware-defined is for each feature that you want to have in your car, like, let's say, emergency braking or a comfort function. I mean, there's in most of the cars today a physical box being placed in the car when the car is manufactured, the so-called electronics control unit. And that electronic control unit drives that function. But it also means that the car is pretty static in the features that it has. And I mean, that makes the car basically age from the moment you buy it. What it results into, if you look into how the car is built, it's all these boxes now also need to be connected to each other, and it results in this kind of tremendous mess of cables in the car, different buses that run throughout the car. Now, what is the industry working towards? We're working towards a software-defined vehicle, meaning that software determines the function that you will have in the car. I mean, I know there's cars out there that are much more in that direction already, but definitely not everybody is there, and there's still plenty of challenges to solve here. But moving to a software-defined vehicle also means you move all of the compute that was in the past in 200 different ECUs in the car, you move it into a centralized vehicle computer, a single computer that runs all of that functionality ideally. That also enables a lot of scalability on the software workload that you run. So what we're looking for in a future vehicle is really a centralized vehicle computer that now, because you aggregate all of that compute, needs to show data center performance. It's running a lot of, let's say, driving functions, autonomous driving or driver assist, but also user experience inside the vehicle, driving a lot of displays, so really data center performance. Needs to be very power efficient because it runs on a battery of the car. If it would consume, let's say, 1 kilowatt per hour, the average driving speed of, okay, I'm European, so kilometers per hour 50, it would mean like 2 kilowatts per 100 kilometers. So that's a significant amount of the battery capacity. So we need to make it power efficient. Means we need to build that compute in an advanced node. It needs to be very cost efficient. Cost is always a concern in automotive, and needs to also be very reliable and safe. Since every function now runs on that single computer, you don't want the car to be stuck in the middle of the road. If that computer fails, that would really be a problem. If we look at how the compute has been evolving in the car, going back 10 years, a bit more as 10 years, no, 2011, a chip that typically went into a high compute function in the car, and at that point in time, this was your infotainment device with a nice map display and so on. This was a so-called IVI SoC. That was an 80 square millimeter chip built in 40 nanometer. Fast forward to today, in that period, computer vision has been replaced with AI, and that AI functionality has been growing continuously. Today in a car, you would find a chip that was introduced in 2022. That is 455 square millimeters, has something like 250 TOPS available, and is built on 8 nanometers. So that has become a pretty big chip. So not just Moore's law, which would allow us to print more transistors by doing more denser nodes. We actually also had to grow the chip to really get enough compute in the car to drive the functionality. And it doesn't stop here. We really see a need for a continuous growth of compute in the car beyond that 450 square millimeter. And I mean, I think the audience here knows that when you start building these chips as large as 450 square millimeters, you'll start suffering from things like yield, okay, not considering repair capabilities. So that's going to be a challenge to continue to grow that compute in a monolithic fashion. Another problem that automotive has, I think it was mentioned before, it's definitely not the size of other markets in the sense it's definitely not the size of a mobile phone market. So globally, it peaked around, like say, 100 million cars that was produced globally per year. but actually today we're more looking at 90. So we think we've had the peak there. So probably the amount of cars produced per year will only drop because of different changes in mobility as a service. Those kind of things will probably mean that there's going to be less cars built, which may be a good thing. But it also means that, you have to, if you think about the compute that you now need to build for these cars, and you would want to build that just for the automotive segment, I mean, and you need to build it in an advanced node because you need the compute horsepower, and you need also the power efficiency of such an advanced node. It becomes unaffordable for the automotive industry. So that's really a challenge that the automotive industry is facing, and this is also a reason why, if you look at the companies that can still provide that high compute in a car, there's not that many companies left that actually do those kind of chips. There's plenty of companies that still are doing electronics in a car for more of, let's say, embedded type controllers and so on. But really on the functions that drive the ADAS, the high-end IVI, there's only a few companies left. So coming into chiplets, I don't think I need to explain to you the benefits of chiplets, but let me maybe reiterate some of the benefits of chiplets that we definitely see as very useful in automotive. It's really, for instance, that composability and reusability. Not every car is built the same, not every car is a premium car. So using chiplet technology, the fact that you could compose it, that you could decide, okay, I put a number of CPU cores or a number of AI accelerators on this particular product instantiation because it goes into a premium car, that's really a good feature to have. Also the fact that using chiplets we can actually scale beyond that 450 square millimeter boundary, that's really a good property to have because we need more compute, we need to grow beyond that 450 square millimeter. And then I think the gentleman from ANSYS, one of the previous speakers, had said on the heterogeneous nature of these chiplets, that's actually also really a very interesting property. The I/O chiplet, for instance, on this diagram, connects to the vehicle network. The vehicle network today runs between, let's say, 1 megabit to 100 megabits for the lower speed buses, up to, let's say, maybe 10 gigabits. You don't need the most advanced node to actually build that silicon. You don't need to build it at 3. Actually, you don't want to build it in 3 because then it needs to also survive ESD and so on. So probably that I/O chiplet would be built in a more mature node, whilst the VPU, something like a vector processor, an AI accelerator, you want to build that in a very advanced node because you want to get the maximum performance at the lowest power out of that particular chiplet. So that's, again, really an area where we see lots of benefits of chiplets in automotive. Yeah, so so this is really something that resonates well also with the OEMs, but how do we get there? So how do we get to this idea that I can build my product, my compute for the car using chiplets? And it's also been said before here, like, I think if you look today, I mean, there's companies out there building chiplets, and the way most of these companies build them completely in-house. So really single design entity makes all the decision within a single engineering team on all the interfaces. Maybe they use UCIe, but then even with UCIe or a bunch of wires, there's probably a bunch of things that are not completely resolved, but having a single engineering team, they can make all those decisions and the product works. What the automotive industry really wants to get to, and I think many of you also want to do that for other market segments, is really this kind of idea of an open Lego brick-like chiplet ecosystem where you have a set of GPUs, a set of CPUs, a set of AI accelerators, a set of I/O, and you can freely combine them with each other. Now, that's a cool vision. Unfortunately, I fear that we're still quite some years away from that, but definitely what we require to get there is initiatives like this to standardize on those interfaces and also the physical form factors and the packaging technology. So we really need to have a strong standardization for this. And I mean, this is something we're very, let's say, happy to collaborate and work towards. In the meantime, probably we'll see some first instantiations of chiplet-based designs appear in the market, also in automotive, where it would be more in the nature of, let's say, a single, let's say, anchor SoC, maybe complemented with a specific purpose-built AI accelerator or an I/O chiplet for automotive. That might be, let's say, a pragmatic first step. Now, looking at that vision towards the open automotive chiplet, we looked a little bit like where are we on readiness? This was something we've done 2 years ago. We looked at many aspects, and okay, they're unreadable in this level, but they categorize a little bit like topics on software, topics on how you physically build these chiplets, topics like the architecture, how do you manage functional safety across multiple chiplets, design exchange, like, can I get a data sheet of a chiplet and how do I engineer with it? But also things like test processes, businesses flow, and also assembly and test. How do you test such chiplets? So we kind of looked at all of those challenges towards the open chiplet readiness, and we kind of create this this sort of a spider diagram which shows, maybe not always very scientific, where we felt that particular requirement was at in regards to, let's say, standardization. We scored it a 0 if nothing was available, and we scored it a 10 if it was perfectly defined. Now, nothing was perfectly defined yet for this automotive use case, so we ended up with something like this. So if we want to get to really this working of an open automotive chiplet, we would have to have a full circle. So there's quite some gaps to solve there still. And we've identified actually those gaps, not just being Imec. We actually organized a number of events that in the meantime are called ACF, so the Automotive Chiplet Forum, with other companies, and we've had conversations and opinions, and this is how we created that graph. And we believe that initiative, so this Automotive Chiplet Forum initiative, continues to be really important for us. And I think here in this community, you're doing something similar, maybe for a different use case vertical, to really hear from all of the actors, like where do they see the challenges and what challenges need to be solved towards hitting that goal. Actually, last week we had the 4th time that we organized that event, and the event is open to everybody. First time in the US, but the 4th time we organized it, and it was hosted by KLA in Ann Arbor. And again, it was a big success. We had 140 companies there. So it continues to show that there's a great interest in this topic of automotive chiplets. But again, we're not there. We still need to solve a number of problems. We will continue to do that, and Imec has started also this STAR initiative, so really an initiative to continuously look at what kind of innovation is still needed in the car to actually get to such an open chiplet ecosystem, but also other electronics innovation. Okay, but maybe a bit more detail, like if you looked at that spider diagram, the problem with such a big group of companies is, you can discuss everything, but really going deep, building the standards requires effort. That was also said before here. It requires, strong volunteering or strong research to get to some results and to really dive deep into some of these topics. And this is, I'm not sure to what extent you're familiar with Imec, but Imec has been advancing the CMOS scene for the last 40 years. And we've always done that. There's a need to research a certain topic. The research is expensive, and the way Imec has always solved that is by, partnering up with a number of partners that are all interested in that research topic, and then they pitch in an amount of money that enables us to do the research. And that's what we're now also doing with this automotive chiplet. So we've decided, like, on this area of the physical and the QNR, which is a main concern. So chiplets can today be built maybe for a data center, they can be built for a mobile phone. But if you really use the chiplet technology with the microbumps, with the silicon interposers or the RDLs, will it really survive the automotive use conditions, which are -40 +85 ambient, humidity? We're not talking even about 15,000 operational hours anymore, which used to be the old automotive, but we're talking about 50 to 100,000 operational hours. So can this chiplet technology really survive those use conditions? That's a major concern of the OEMs. And that's one that at Imec, we do some dedicated research. We're building a prototype of such a package, and we're putting it through an automotive qual cycle, and we will get some results on where it's failing. And then the other topic is really on the architecture, and it's about companies were used to build SoCs with an engineering team with sourcing IP, but now I source chiplets. It was a little bit this maybe dating versus marrying topic that also was addressed earlier here. It's like, how do we make sure these chiplets actually talk to each other, but not just on the main band traffic, but also on things like, for instance, boot images, authentication. And by the way, boot in a car means when you put on the ignition, the car is ready in a second, not after 10 minutes, which may be acceptable for other markets. So those kind of topics we really need to look at. And that also yielded in a dedicated working group within Imec to look at those topics. So, like I said, like the way we do that, so that's going deep within Imec, we do that in a program mode. So we collect a number of partners that are all jointly interested in this research. And I'm happy to, let's say, announce these are our first partners that signed up to it. And Bill Chen was here earlier. Also very happy that we have ASE in this program with their knowledge on advanced packaging and trying to meet the automotive use conditions with that. Now, so this is our program, but maybe going back to that overview on the challenges, like as you can see with our program, we're not covering the whole pie. I would like to applaud also some of the OCP initiatives on the, for instance, the CDX format. The UCIe has in the meantime created an auto working group. So we really like to look also at other industry initiatives that complement that pie, and also understanding that, for instance, you had the open chiplet economy as a topic here within OCP. That fits to me in the business side of things. So I really appreciate those kind of synergies. So collectively between, let's say, the initiative here, the ACF and ACP, I hope that we really get towards this vision of the automotive chiplet and really enable the value of chiplet in automotive, yielding a scalable performance at reduced time to market, chiplets that meet the automotive quality, reliability, and safety, and that are really resilient, that provide also a resilient ecosystem, so that we, let's say, have an ecosystem of chiplets rather than, let's say, 2 SoC suppliers. We now have a chiplet ecosystem of hundreds of IP providers that can all pitch in their chiplet and build the systems that the OEMs need. So with that, I would say thank you, and I'm not sure if there's time for questions.
We have two minutes for questions. Any questions for Kurt? So I have a question. You know, a lot of talk is basically about the computer in the car.
Correct. Yeah.
The ADAS systems. Now, the computer gets data from sensors and other chips which are buried in a million other places in a car. So is the target to go for chiplets just addressing the one ADAS system, or are you looking at more than that?
So this centralized computer has a big challenge, and we think chiplets is definitely a solution there. It doesn't mean that chiplets would not be used elsewhere in the car. To your point, for instance, a radar unit, that would also be a very interesting candidate for chiplet packaging technology. The analog front end built in a complete different process node versus the digital back end. So that could indeed be, but in the program we really focus on the digital compute engine and how that will be built. Yeah.
Right. Do you think that once you've figured out some pieces of that, you would move to the other more also obvious pieces that could benefit from heterogeneous integration?
Yes, and I mean some of the conclusions will be valid there as well. Like when we look at packaging technologies or interconnect technologies that pass here, they will also pass for the other application. Yeah.
Thank you very much.
Cheers.
Hi, I got a question or a comment. I am from OpenChip, a startup in Spain. Before that, I spent quite a bit of time in automotive, on the GPUs for automotive. Having moved recently to HPC, I see a lot of demands in terms of performance, yield, that can go even beyond what is required in automotive. In some of the presentation, they say how costly it is to lose a bit of data in terms of training. So the comment I wanted to make is HPC might have requirements that apply to automotive more than the automotive industry might realize in terms of level of performance and security.
No, absolutely.
Not
no, absolutely. And I think, back to the market size of automotive, we believe that the chiplets that end up in the car actually need to be chiplets that were designed also for other market segments. So we need to find ways of making these chiplets that are also that maybe come from other markets, work in an automotive condition environment, and meet the automotive use conditions like reliability, functional safety, and so on. Absolutely. Yeah.
Yeah, thank you. I was wondering if you could just say a few words about maybe the fault tolerance and redundancy requirements, because obviously when you're in a moving vehicle, you really
Yeah.
don't want that processor
No.
to fail. So
Yeah.
do you have to really double everything? Or?
Yeah, absolutely. So it needs to be super reliable from an availability perspective. If a compute engine, one CPU core dies, I mean, and the car will be stuck, that would be bad. So I think we need to put in redundancy and number of compute and also the operating system support for that. Also on the interface, if a micro bump cracks during the operation, I mean, we should find ways of actually making sure that that gets mitigated in some way. It is a big concern, and how it's solved today is typically indeed with redundant compute units, where one can take over from the other, because you have 200 of those, and maybe a few of those are doubled. But going in here, we really need to look carefully at, okay, how do you build this using chiplets, and maybe indeed the solution is also like on the picture a little bit. You would have maybe two system and package complexes that are somehow working in tandem mode. So if one goes down, the other one at least can take over the critical functions and make sure that the car gets to a safe stop or a safe pullover.
Okay, time for one quick question, because we're already 2 minutes late, but go ahead.
So the way I look at automotive as a ecosystem, where we have a number of microcontrollers talking to each other over a kind of CAN bus. So basically, what we have is there are multiple attack vectors that are possible. You can look at, for example, the way we address this issue in the OCP is basically we have a platform root of trust that brings the whole data center out of reset into a secure state. We can think a automotive also like that, in the sense that we have a number of microcontrollers, and when you put, like what you're giving the example, then when you put the ignition and you want to start your car, and you have to boot all the microcontrollers that are running in the car, right?
Yeah.
So I was just wondering the kind of security issues that have been addressed by the OCP in the data center aspect, can it be used for an automotive?
So cybersecurity is definitely a very important topic, and indeed there has been attacks on cars using physical access to the car, but also remote access. I mean, physical on the CAN buses and so on, I mean, they have been designed in the 80s. I mean, they don't have encryption on the bus itself, so we want to get rid of those buses, and this is also where you see a transformation of the fabric in the car away from CAN buses towards a more of an Ethernet-based core fabric, at least. I mean, there's still going to be CAN buses to the edges, but an Ethernet-based core, and then employing encryption on that. Towards the actual cloud and so on, also cybersecurity is an important topic. Now, I don't know exactly how it's done in OCP, so I cannot answer whether that's good or bad.
What I was trying to come to that, we should look at a car as a single system, single platform. We not think in terms of, say, number of this microcontrollers.
No.
Single system, and then single system has a number of attack entry points, because there are a number of controllers talking to each other. So that way we can think very similar to the data center, where we have number of devices that goes into a server platform, and then we have multiple attack vector possible. That's why they have introduced a concept of platform root of trust that orchestrate the whole boot process, secured boot process in the data center.
All right.
Yep. I think we might have to take this conversation offline. Thank you so much, Kurt.